So to remind you, we have 2 talks now, 45 minutes each. Then we'll have lunch here. And then we'll come back here for a discussion. Free-wheeling discussion. Life, the universe, and everything.
So first, I would like to thank Moshe for the invite. It's my honor. And today I will talk about quantum program verification, automata-based approach. Apologize that this is not relevant to games yet, but I hope after this week, your name will be here. We will work on games. And one message I want to say is that it's not that far from what we can do. Like my background is almost the same with all of you. So I will begin with some motivation why we are interested in this. As we know that the quantum computing, they are very powerful. They promise things that we cannot do using normal computers. For example, it promised to break cryptography. And then in different fields, like they develop algorithms for using the power of quantum. For example, they have quantum machine learning, use it for optimization problems, and they use it to simulate the chemistry behavior. And all rely on these hardwares.
What is under fast?
Under fast development. From here.
Under fast is good or bad? Not sure I understand it. What is under fast? Developing fast?
Yes. Under fast development.
The development is very fast.
Under fast development. Okay.
Yeah. Sorry for making it very vague. Yeah. But why this is relevant to us? Because in order to control this complicated hardware, actually, this quantum hardware, they need software control. Like there's a huge software stack to control your hardware, starting from the programming language, like let's say in Q#, Qskit, etc. You want to compile it to the instruction set that can be run on the computers. For example, this IBM computer, they can support this quantum gate, and the Iron can support this quantum gate. You can just think this is CPU instruction set. They have different hardware. They have different instruction sets. And in a programming language, it usually allows the largest set of quantum gate, and you have program constructs like if and while. And so you have compilation, like compile your program to a circuit and then run it on the hardware. And along this software stack, there's a lot of research problems, and then this is why this is relevant to us. We want to work on quantum software, and we can do verification, and then there are optimization problems. So we have the compiler validation, and then we have simulation. You can run the circuit on a classical computer to see the small cases to see how it behaves. So this is why it's relevant to us. And so today I'll talk about verification. So why I don't think we need to motivate why we need verification. And this is particularly important for quantum because it has probabilistic behavior. Every time you run it with the same input, it gives you different results, make it difficult. And also when you observe it, for example, you put the assertion in your programs, observation will destroy the state. So that's another reason why the classical approach for ensure software correctness is no longer that useful in a quantum setting. So form verification is one of the promising approach to help with quantum. So give you a little bit the example of the test of verification problem we want to handle. So it's a pre-post condition style. This is a quantum circuit, but content is not important for now. So you can put the precondition, let's say start from some default initial state of quantum, and then you write the post condition. In this case, you find the hidden string 110. This is a brainstorm by the any algorithm. And so it's basically from some initial state and then go to some post condition. If you give these to our tool, we can from a precondition and post condition. This is a quantum circuit in the OpenQASM format. If you run it, you can show that okay, in this case we have 4 qubit and 10 gate quantum gate, and you find that you can verify the circuit with some time. And if you change one gate, then you find okay, the verification failed. Everything is done automatically. So this is what we are going to do. Basically, a symbolic verification of quantum circuit and programs. So just now, after motivation, I'll give you the outline of today's talk. First, provide you some quantum background, so no worry that you don't need any quantum background to understand this talk. And then I talk about verification. So to begin with, so this is a classical state, 3-bit. So any Boolean assignment, this is a state. So why is this is a classical state? Then what is a quantum state? It's actually a distribution over classical state. So all assignment has a probability. That's how we can build a quantum state. So every time when you observe it, you maybe get, according to this probability, you get one state. So that's why every time when you observe it, you may get different state because it's a superposition of the classical state.
It's not 100%.
So yeah, it should be. So I have that here. It's hidden. And one way to build it is we can actually build a quantum state as a decision tree. So each branch corresponds to a classical state. And then here is the probability. So that's one view. The quantum people, they usually like to build this as a vector. So this is the tree leaf that we have. But building it as a tree is another option that we use. And why you want to build it as a tree? Because now the quantum gate, basically this is, you can imagine this is the counterpart of the instruction that we have for classical programs. So these operations, they can be built as tree transformation. This negation gate, X gate, if you apply it on the first qubit, what happens is that you just swap the left and right tree. So after you do negation, now the original left becomes the right one. So the red goes to the right, and the green one goes to the red. This is the negation. And the other quantum gate is the Hadamard gate. This is more complicated because you need to combine the left and right tree in some way. In this case, if you apply Hadamard to the first qubit, you need to combine every corresponding branch in the red and green trees. So on the left, it becomes the sum of them. On the right, it's the subtraction. So maybe the font is too small. This is A and this is E. We just focus on the left branch. So this becomes their sum. And this is the minus. And we have divided by square root of 2 to normalize it. And I simplified it a little bit because they usually call this as, it's not really a probability value. It's a complex number where the absolute value square is the probability. So it determines the probability, but actually it's a square, absolute value square. So that's why here I normalize it with square root of 2. This is another quantum gate. So the message is, and this is a control NOT gate. So it says that if the first qubit, so this is an example of control NOT gate on X1 and target X2. Its meaning is if X1 is true, then I apply the NOT gate to swap the red and green. So this is the control NOT gate. So if I apply this C NOT gate here, so the left right will be swapped. So I get the other tree. And so why quantum can be helpful for classical computing? Because we have this quantum parallelism. So you see that now we apply one gate, and then you can update exponential remaining classical state. So that's why quantum is powerful, because sometimes it can promise exponential speed up. One operation can update the exponential remaining classical state. And so it's also like at most they can provide the exponential speed up. And this is how the two subsystems are composed in the tree view. So we have a state here. It was a system 1 and system 2. The composition is I just rewire the root of these to every leaf over here. So the leftmost branch now becomes, the probability is the multiplication. So if I have the first system A, the probability A, and then this one is A prime. So the new composed system, I have AA on the leftmost. Basically just rewire this to all the leaf nodes, and then the probability now I do a multiplication. And one thing, probably you heard about it, like quantum entanglement, but in the tree view, you can see it very clearly. what do we mean by quantum entanglement? These are two maximally entangled states. So this one, the tree is I have 0, 1. It has some probability. In this case, it's 50%. 1, 0 has another 50%. And why this one it has maximum entanglement? Because if once you know the value of x1, if x1 is 0, then for sure you know x2 is 1. If you know x1 is 1, then for sure you know x2 is 0. So this one has the strongest entanglement. This is a similar stuff. Only 0, 0, and 1, 1 has probability. So if you know x1 is 1, then x2 is also 0, then x2 is also 0. This is how you can see quantum entanglement. Under the tree view, you can see many things. And what is a quantum circuit? It's just, under our view, it's just a sequence of quantum gate tree transformation. So if you have a lot of, a circuit is just a sequence of gate. And the semantic is just a sequence of like tree transformations. It's an updated quantum state. And so at this point, you can already do something. Like so, if you want to simulate the behavior of a quantum circuit in a classical computer, it's just a sequence of the tree update. So for this one, this is actually the behavior of the so-called EPR circuit, EPR generation circuit. It generated the maximum entangled state that we just saw it. So it's first with Hadamard gate and this control NOT gate. This is a control NOT gate.
But why should I not just think of it as a probabilistic program?
Oh, because actually the tree leaf is a complex number, and why we need it, because you need sometimes to describe, this is from Scott Ellison, like why they need the complex number as it's not really a probability, it's a complex number where the absolute square is the probability. And the reason we need the complex number is sometimes you need to describe the negative interference, like this double slit experiment. Sometimes like the probability when you put together, they need to cancel out. I just copy what Scott said, because I don't understand the physics part that much. But the physical people, they need the complex number to model the probability. It's a value that can determine the probability, but I mean, in order to for example describe the negative interference, they need complex numbers. So it's not just a probabilistic program. And one thing that is already relevant to us is if you want to do simulation, we describe one tree as a decision diagram. Actually, this is what the EDA people do. In the EDA conference, there's a lot of paper talk about quantum simulation. And what they did is essentially like using decision tree to describe the quantum state, and then you can do simulation. And here is already becomes the first problem. Actually, that's the starting point. I started to work in this field. In classical setting, we use one BDD to encode a set of states. Like each assignment is one state. Here, it's a little bit strange. In quantum, one BDD is only one state. Then how do we encode a set of states? It seems like we need another order of stuff. I don't find a good structure to capture it. That's a starting point. We start to think, okay, what can we do? How to describe a set of states? And so next part, we go to verification. Why we need to set up state? In classical whole tree verification, we check against the pre and post condition, and each is a predicate capturing a set of state. And if you want to do verification like automatically against the whole tree poll, then we need a good representation of a set of state. That's why I'm starting to think why we need how to lift a BDD to a set of BDDs. And one solution we come up with is, okay, if we look at what's a good symbolic representation of a set of states, a set of trees. So from automata theory, we know that a set of words, we typically try regular language. For set of trees, one thing to try is regular tree language. So that's the starting point of our research in this direction. So we try to use tree automata to capture a set of quantum states and do the corresponding verification. So this is a very abstract view of what we are doing. So we use tree automata to capture the pre and post condition. And we develop algorithms to compute the post condition after you execute the quantum gate. So this is recall that the quantum gate is just a tree transformation. So we just need to do this for all quantum state encoded here and compute another automata for the post. And you do it for the entire circuit, they get a set of reachable state, and you do inclusion checking. So that's why this is relevant to our research. It's just like regular model checking at this point. So the entire framework can be actually partitioned into three parts for symbolic verification. So you need the representation to talk about set of states, an algorithm to compute the post image, an algorithm to check containment. And for symbolic representation, the thing we begin with is tree automata. So here is one example how to use tree automata to encode a set of quantum states. So these are 8 different quantum states. This is the Dirac notation of a state. So for this particular example, this rate 110, it corresponds to the tree where the branch 110 has a value 100%, and all the others, they have no possibility. So this is one tree, and here we have eight different trees. So actually, the way we use use tree automata is just use the power of non-determinism so far. So here we have from the root state, we have 2 non-deterministic choice. And this, if we take the rate 1, it's actually, if you only read the rate 1, it's 1 BDD. And it corresponds to this particular tree. So if you use BDD in addition with non-deterministic branching provided by tree automata, then you can encode a set of states. However,
I'm missing something. MTBDD give you a rich set of leaves, right? Can be any real number.
One more time.
MTBDD, right? You have a rich. The leaves can be labeled by any real number. Let's say.
Yes, any finite set of numbers.
Well, not really. You can deal with finite set, but we can deal with floating point numbers.
Yeah, but for one particular tree, you have only finite number of.
Yes, but the set of values are all floating point numbers.
Yes.
And that means you need tree automata with a huge alphabet.
Yes, in some cases, but for many quantum algorithms, like the tree leaf is actually they have only very limited number of tree leaves that occurs. For example, the algorithm that they call the Grover search, which we use it to, let's say, solve a set problem. Typically, it has only 2 leaves in the middle of the execution. So for some algorithms, we still have very good chance to have very good comparison. But of course, not for this kind of quantum supremacy example where they have the state is usually not so easily compressible. You need to consider different ways to compress it.
This may be just very stupid because I don't understand quantum. Are the
I try to make you understand so we can go work.
Are the heights of the trees fixed for an algorithm? Like, for example, this one you have a height 3, all trees would be height 3.
Yeah.
And the ordering of the variables will not change.
Yes.
So then there is a one-to-one correspondence between those bit sequences or bit vectors or whatever you call them and the trees.
Yes.
So why do I need to represent trees?
Why do I need to? Because with the tree structure, then it's easier to see you can see common subtrees. It's basically very similar reason for why we use BDD, because we can. For structure, they usually have some shared structure, and then if we merge them, then you can compactly represent one, let's say, set of stuff.
But you would want to actually apply some transformation to a subtree of a tree somewhere in the algorithm then.
One more time.
Something will happen to a subtree of a tree in the algorithm.
Yes,
So then the heights are not fixed. If you do manipulate a subtree, then you're actually dealing with a tree that has a shorter height, fundamentally.
Depending on sometimes it's only target the subtrees. Some depending on which gate you apply. If you apply it to the lower qubit, then it only addresses each subtree at that level. That's true. And but that's only a starting point. I will show you a little bit more stuff. And so here in this particular case, we have these many transitions that to encode 8 different states, like maybe 11 transitions. However, this shows one case that if we extend this to the power of n this many states, then you can encode this set of states using just a linear number of transitions. So this is one example that we can compactly represent a set of states, and this set of states actually occurs in a structure. However, there are some common set of like reachable states that are not so easily representable using tree automata. This is one case that it's a set of the trees that so it has 2 branches has value with value. One is the first bit go to left 0, and then one tree with any one like assignment, this an arbitrary assignment here, arbitrary Boolean numbers, and then this is the one with the reverse, the complement of this. If this is B2, then I have not B2 here. So these two are actually the mirror image of each other. If I want to express a set of trees, here I have exponent 2 to the power of n this many this type of trees for each assignment. If I want to represent a set of trees like this, then I need at least 2 to the power of n minus 1 this many root transitions. Because if I have fewer root transitions, then there must be one root transition that on the left, they can generate 2 different trees. And you see this, all this left and right subtree, I need to have 1-1 correspondence. And in general, this is very difficult. And if I have, let's say, 2 different bit string share the same root, then their right tree then can be arbitrarily combined with the left tree. So it's no longer this 1-1 correspondence no longer maintains. So this is not so easy with tree automata. So we started to think about a variant of tree automata that suit better for quantum. This is the automata we developed. We call it label synchronized tree automata. So what we do is we label the transition with a set of the so-called choices. In this case, we have 3 different labels, like choice 1, choice 2, or both of them, they are allowed. And in the same tree run, you can only pick, and in the same tree label, you are only allowed to pick transitions with common choices. In this particular example, you can take a transition root doesn't matter, and in the second label, you can take the 2 red transition because they have common option 2. And you can also take these 2 common option 1, 2 blue 1 because they have common option 1, but you cannot take one red with one blue in this restriction. And with this, you can use this to synchronize because you see these 2 transitions. They model the case where on the left tree, the one branch, the solid one means the one branch, and the dotted one means the 0 branch. The solid branch go to some root, some leaf with value. In contrast, on the right, it's the dotted one, the dashed one, they have value. The solid one doesn't have value, so you can use this behavior to model this kind of image state that we showed in here. And one thing is that the choice, we have a requirement that the choice start from one state. For all outgoing transition, they have this disjoint choice. And this model has the benefit that it has language inclusion is decidable, which is needed in a framework. And also it has incomparable expressive power with standard tree automata. And yeah, why? One hint is because the choice is somehow from one state you only allow this disjoint choice, and then from one label you can only take for one label you can only take the same choice. So for different occurrence of the same state in the same tree label, they will generate the same subtree, which make the behavior somehow finite. In the run, if a state has multiple occurrence, then this definition will enforce that all occurrence of the same state generate the same subtree.
What is the complexity of this non-emptiness?
Yeah, it's actually, we know it's between, so far we don't know, like for emptiness or for
Just non-emptiness,
non-emptiness is p-space.
p-space.
Yeah. But for language inclusion, we only know it's in between exponential space and polynomial p-space. We don't pin down the tight complexity yet. It's not very simple, but in our experience, like checking language inclusion actually is not a bottleneck of the entire verification process under this framework. So it looks like very expensive, but in the experiment, it usually takes 0 time.
0 time?
Yeah,
well,
almost
maybe not 0.
Something that we cannot measure precisely. Yeah, and this might be another interesting example. So you can also talk now. Before you only see like a BDD with non-deterministic branching, but now we show you the power of using cycles. So you get the full power of tree automata. So you can describe this set of states like arbitrary number of 0. So this is, so for n is 1, then you have like the left branch is you have a tree of height 1, and the left go to 1 and right go to nothing. And then for depth 1, so you can have like 0, 0, which means the left 0, 0 branch has something, and then the height is with height 2, and etc. Get the infinite set of these trees. And in this model, it's here like after root transition, the state Q1 and Q0, they have 2 options. If you take option choice 2, then you go to the leaf. And if you take choice 1, then you make another tree label. So in this case, you can describe a set of perfect trees. So this is another power of this model. So we are investigating these models. So this might allow you to do parameterized verification of quantum circuit. So, yeah, this is something that under development only. And so now we spend a lot of time in like how to symbolically represent a set of state, and we will only like briefly mention how to compute the pulse image by giving you a few examples. So I used a different notation of describe a tree automata. This is just a root state is Q, and then you link to these 2 subtrees. If we want to apply the negation gate on the second qubit, let's say, our algorithm is very simple. We just look for all the transitions with labeled X2 and swap the left and right. That's the X gate. And for another set of gate like Z, ST gate, what they do is essentially they multiply the right subtree under some qubit with some constant values. So just multiply the right tree with some constant value. So what we can do is we just make a copy. So this is the original transition system. I make a copy, so I get the blue version. Now I multiply the tree leaf with the desired number, and then I jump, like from this qubit, I jump to the blue version. So that's a construction for this kind of set. They multiply the branch with some value. It's a complex number, so and this complex number is guaranteed that the absolute value is actually 1. So that's the quantum gate operation. And containment, like as we said, in the standard tree, please.
You mentioned post. What about post star?
Post star. So far we only handle finite programs. So post star is just compute one after the other. Because quantum circuit is just a sequence of like a gate, so it's really just one after the other. So far we don't have a loop, and we don't have branch. I will go to that like a little bit later. And yeah, so containment, you just do the standard tree automata language inclusion algorithm, and then for the extended one, we have like an extended algorithm for that. But I will not talk about it in this talk.
But is this model closed under complement? I doubt it.
No, it's not. It's not.
Containment usually containment usually includes complementation.
Not really. We do some kind of this kind of on-the-fly construction. We do some on-the-fly algorithm, on-the-fly subset construction. So it doesn't really like need to compute the complementation. It's funny that the complementation is we know it's not closed under complementation, but we have an on-the-fly algorithm to check the inclusion. Because you see let's say one characteristic of this model is for the same tree occurred in the same tree level, they will generate the same subtree. So you only need to, if a state occurs multiple times, then you need to remember one, because you see, like if the state Q that occurs, maybe I can go back to here. If I have a loop and then in some run, this Q plus minus state occurs 3 times, because all of them they need to take the same choice. So all of them they will generate the same subtree. So you only need to remember like okay, this state Q occurred there. You don't need to remember how many times it occurred. They will give you the same subtree for emptiness testing, let's say.
I have to say, I found it very counterintuitive, because to me it seems once you have level synchronized, you're very close to context-free languages. And so my intuition is context-free languages, everything is undecidable.
Yeah, but this one is decidable. So
that's why I said I'm
I would like to see a little bit.
I'm in an uncertain quantum state.
Actually, if you look you have the perfect information, you have the entire tree, then you have no uncertainty.
The tree is not fixed height because the number of variables depends. Yes, it is fixed height. It depends on the number. Okay, so you're doing it for a specific number of variables. So it's a fixed height tree. Okay, so you're right. Maybe that's the key thing here. Yeah.
So one more time.
The automaton model is defined not for a fixed height. I'm not in the context of quantum circuit verification, but
for this one, it's not really fixed height, because you can have every height. So we have this kind of unspecified height.
So it can have infinitely many trees in it, right?
Yeah, this one can. This one of arbitrary height, but with with a specific structure, I would say. This one
Can
they
represent a family of quantum
states. Yeah. Sorry.
So you can represent the states of a family of a quantum circuit, not.
That's what we are trying to do. Like we also want to develop allowed like a few. Now currently we only allowed a few like fixed types of parameterized quantum gate. For example, apply certain gate for all qubits. By combining these, we can do some limited types of parameterized verification.
Are there some quantum circuits that you cannot? Which you cannot analyze the states? There are some.
Yeah, so far we have a lot of like, for example, we show you this Hadamard gate. Sorry, I need to quickly go to something. So it will maybe this one is better. Some quantum gates they will introduce some like for example square divided by square root of 2 in the leaf. And if you do this parameterized, you will get infinite many like 3D. So we have some idea of how to handle this kind of thing symbolically, but it's not done yet. A lot of questions we just started. Maybe I should discuss more like offline, like why the containment algorithm works. Maybe after discussion you'll find a bug. Who knows? Yeah, but yeah.
We can also propose, like we have relatively free afternoons. So like we used to have like someone would say, okay, I will discuss something on the second floor at 4, and then you can go into more details if you want.
Okay, good. Maybe I can describe the algorithm if you are interested later. Now probably we don't have enough time to give you a little bit more stuff. So we also allowed the version I showed, because it's tree automata, so I have only finite many like constant allowed. But we can extend this to use variable on the tree leaf. So in this case, you can describe the patterns. For example, I have V high means that this is some high value and some other low value. And you can do very similar thing, the quantum operations, but now symbolically update the tree leaf. And you can check with against this kind of predicate. Like we say, after you run the execution, you get this particular tree. This is after symbolic execution. And I only show one tree, but we do it over automata. You see, this is the result of the symbolic representation. And then in the spec, we have this kind of, underneath, we have predicate. And a tree is allowed by a predicate if when I fit all the leaf into a corresponding position of this square of the leaf, this is a valid formulae. So this is a symbolic extension of the framework. It's allowed you to check, for example, we call it relational property, because if you have only preposed as a set, you cannot describe a relation. But here, it gives you some power of describing a relation. Relation means that I cannot see this state, it's actually come from this state from the because it's maintained as a set. So using variables, you can describe some kind of relation. So I can say that this state, the probability of this correct answer is increased after I run the circuit. And this model is actually different from the symbolic automata model that we are familiar with, because now the variables, we force that all variables, they need to be assigned the same value. So we have variables on the transition, but the semantic is that after you get the symbolic tree, then you need to have any valid assignment to the variable give you a concrete tree. So that's our semantic or symbolic model. So all the variables occurred in the same structure. They will give you they need to be assigned the same value. And so now I go back to program verification. So we need to talk about still how about if we have branches, we have if else, we have loop. So quantum program is actually the quantum circuit that we already see, and then with probably a branch structure and with loops. So here can be one example. So we apply Hadamard gate to the first qubit and control NOT gate. Like the first qubit is control and the second is NOT. And we can measure the value of the first qubit. If the first qubit value is 0, then I run X1. Otherwise, I just go to the next line. And for this is I measure the first qubit. If it is 0, then I do the loop. So here I have infinite programs with allowing conditional statement and loop. And what's the behavior of this conditional statement? So if you measure the first qubit, you check the value of the first qubit. If the measured value is 0, then what happens is that the first branch is for sure 0. So the tree that's why the observation will destroy the quantum state, because now you know the first qubit is for sure 0. So the right tree has no chance. So only the left tree has probability. That's after measurement. But actually, you still need to do some normalization. And normalization is actually not so easy if you apply it at the automata level. You need to normalize it for all possible trees encoded. So one choice that we take is we skip this normalization, but we somehow leave the inclusion algorithm to support the matching of trees that are equivalent up to scale. This is also some ongoing direction that we are trying. So with this, we can do measurement. The measurement just corresponding to another kind of symbolic execution. And if you can do the measurement, then you can handle a program with loop. We require you to provide the invariant at the moment as a tree automata, or extended version of tree automata. If it has this invariant, then what you can do is you from the precondition, you can just do the gate operation symbolically and check whether this is contained in the invariant. And then you check the usual thing, like from an invariant, if the measurement value is 0, after you do a loop body is included in the invariant. And after the loop, it's satisfy the post condition. So this is just the standard things. If you can do measurement, then you can do loop. So that's how we can handle infinite program structures. So that's what we have so far. So like the message is like we have actually it's not completely irrelevant to what we know, and then there's a lot of space that the people can do, like do verification, do compiler validation, and we know that simulation is just BDD operations. So this is also something that we know how to do it. So we can actually do quantum, and there are plenty of research problems that is possible. There's a link. Yeah, that's the message I want to
No. So can you verify Shor's algorithm?
No, because Shor's algorithm, they have combination of, there are a few reasons. There are combination of classical part and quantum part. And so far we only handle the quantum part. This is the short answer. And then the other is that the tree generated by Shor's algorithm, actually they have Fourier transform inside. And then it will generate, this is one case that they generate too much deep state that we cannot model like efficiently. We need different symbolic representation. So there are some ideas, but it's not done yet. Cannot.
Okay, let me kind of repeat my earlier confusion one more time. In the circuit case, you're always finite state other than the labels that Moshe mentioned, the complex numbers. If we ignore the complex numbers at the leaves, it's finite state. Or
Even the complex number, it's actually finite.
Okay, I don't want to even think about complex numbers.
It's just not symbols, finite symbols. It's
So-
not. It's just symbols, nothing else.
So then I would have expected you to mention something about compactness of representation all along, rather than, as in, we are doing this, we kind of put all these states together because it's a compact representation, right?
Yeah. Here, there's maybe I did it too quick. Here you see that we have, in this particular example, we have 2 to the power of 3 in this many state, and we have like 11 transition to encode. And in the next slide, if we extend this to arbitrary Boolean combinations to n qubit, let's say now you have 2 to the power of n state, and you need only 3n plus 1 linear number of transition to encode this particular set of we call it computational basis state. So this is one example that the 3 automata can compactly represent a set of states.
Okay, but do you have something like other than here is an example, something more general, as in, because it seems like you're not playing with order, right? The order of the bits remains the same, so the same ordered BDD stuff doesn't apply.
Yeah, it's very similar. Like so far, the order is very similar to what BDD is using, I think.
But you don't change the order, right?
I don't change the order. I can. There are also like similar algorithms. It's actually you can apply similar algorithm with BDD to do the variable reordering. But I don't talk about it at the moment. We have some. It's the same algorithm for variable reordering. You can also do it.
And other than this theoretical result, you have observed that for the algorithms that you verified, if you were to just use a DOM representation, there will be an exponential blow up?
Sometimes there will be exponential blow up, of course. Like it's again like very case by case. But so far, I would say that the performance is quite like in the set of benchmark we tested. It's comparing with other tools. I think it's quite nice.
We'll postpone more questions to the afternoon. But in the afternoon,